Hello everyone, my name is Michael Lindemann and I'm here today to talk to you about our paper called Machine Learning-Based Protection and Fault Identification of 100% Inverter-Based Microgrids. This was a co-project between the University of Alaska Anchorage and Virginia Tech, and the project as a whole was funded by the National Science Foundation. So as we see more and more renewable penetration into the electrical grid, this brings along with it greater inverter-based resources integration with the existing electrical infrastructure. And so fault protection of grids which are largely composed of IBRs or inverter-based resources can be more challenging than in grids that are comprised of only, say, synchronous generators. And that's due to the IBRs having a lower short circuit current than typical synchronous generators. This lower short circuit current can lead to stability problems for the grid, and therefore it's important to be able to detect when there is a fault and de-energize the line so that overall grid stability is maintained. We decided to focus on using a machine learning-based short circuit detection and fault type identification for inverter-based microgrids in this work. So here's the grid that we implemented. It's a 4-bus fully inverter-based microgrid. There are a total of 4 inverters, with 2 of them being in grid forming mode and 2 of them being in grid following mode. Here you can see some of the parameters for the grid. And so here is how we actually created the data set. We ended up using the Python API for PSCAD to run a multitude of different fault simulations with differing fault types, locations, fault resistances, and fault durations. This gave us 420 cases to use for training and testing. After we had created all the cases, we then assigned a fault type numerical designator for each of the cases, and the machine learning model would need to be able to predict this numerical designator. So 0 would mean like no fault, nothing occurring, and then 1 through 7 were the different types of faults, A to ground, B to ground, that sort of thing. For an algorithm, originally we were actually looking at a support vector machine algorithm, a SVM model. However, we ended up finding that SVM models scale quadratically or cubically with their training data complexity. And so given that our data set was sampled at 1 millisecond, this means we had a ton of data to go through, and an SVM model just was not practical. We wanted this to be able to run on off-the-shelf microcontrollers, so we ended up going with a decision tree model, which is essentially just kind of one more step up in the hierarchy of machine learning models. And so with a decision tree model, the model could still be very small, so it could run on a microcontroller, and it could run every few milliseconds on even a small microcontroller like, say, a Raspberry Pi or that sort of thing. So in order to create this decision tree model, we used the scikit-learn library in Python, and the decision tree had a maximum depth of 43 and had a total of 4,044 leaves. The input variables consisted of current, voltage, P, and Q from that bus 1 again. And so the data was split using the train test split function in scikit-learn. We used a state seed of 20 for repeatability so that we could do this again in the future if necessary. So for our first case study, we'll look at a to ground fault, and this is the fault type 1, and this was located at bus 1. So as you can see, the decision tree model overall did really well. There's only one point during the fault where the decision tree model essentially became unsure and wasn't quite certain whether or not there was a fault or not, and so it oscillated down towards 0. But as you can see, it recovered from that instantly, and overall it tracked the fault extremely well. Next, we'll look at an A and C to ground fault located at bus 2. Here again, you can see the model actually did even better than the first case that we were looking at, where the model tracks this fault almost exactly. And so if you notice on the fault type plot down there at the bottom, the fault type immediately goes to 5, which does correlate with an A to C to ground fault. So again, almost perfect performance here from the model. So this last case study is actually a really interesting one. We wanted to throw something a little bit different at the model to see how it would react. If you notice, the fault type or the fault resistance here is 40, and the model had never seen a fault resistance of 40 before. In all of our training data, there were no 40 resistance or 40 ohm resistance faults. And so we wanted to see what would happen if we just kind of tossed this at the model and see how it performed. As you can see, there was some oscillation towards the beginning of the fault. However, by about the 0.1 second mark, the fault had the machine learning model had totally determined that there was definitely a fault occurring, and it held that all the way through to the end. In conclusion, we think that this machine learning based method really shows its value. We think that the fact that it trains in less than 9 seconds makes it really applicable for real world applications. And more importantly, it doesn't rely on communications, which increases the resiliency against cyber attacks, and it also negates the effects of communication delay in detecting a fault. And so we think that the fact that it can detect both the fault occurrence and clearance of fault is very important as well, because this means that maybe you could set some sort of designator to where if a fault occurs for more than, say, 16 milliseconds or something like that, right, then the protection would then kick in. But if a fault clears itself, which sometimes does happen in the grid, then you wouldn't lose that whole section of line, right? So thank you again, and here's my email. If you have any questions, feel free to shoot me an email.